Hello! Today we're going to put the standard normal distribution to one side and look at some non-standard normal distributions. We've done loads of calculations and it's all going to be really crucial and useful because it's just going to be a similar sort of thing for these non-standard ones. Here is the formula for a general normal distribution. This guarantees that we get an area under the graph of 1, hence it's a probability distribution. We have a bell-shaped curve focused, not focused, but centered at mu. That's the mean, that's the median, and it's also the mode. And we get different shaped normal distributions, and that's where this standard deviation comes in. Before I say any more, I think I'm going to show you one. So actually I did say we're not going to look at the standard one, but this is our starting point. Here's the standard normal distribution. It doesn't actually touch the x-axis, it's just it becomes so small that it looks like it is. Now, I want you to think, what happens if I increase the mean? What's going to happen to the curve? Okay, let's have a look. So if I increase the mean, it moves in a positive x direction. If I decrease the mean, it moves in the negative x direction. I hope that makes sense. Seems okay to me. Slightly harder question, I think, is what happens if I change the standard deviation? What's going to happen to this bell-shaped curve if I increase the standard deviation? Right, I wonder what you reckon. Do you reckon it's going to get thinner or fatter? This is what happens. As we increase the standard deviation, it's going to spread out because we've got a larger spread of data. That's what the standard deviation is measuring. And you can see the peak is going down because we still have to make sure that we've got this area of 1. So there we go. And if I could keep increasing it. I can't in this GeoGebra file. If I keep increasing it, it'll get more and more spread out. It will still be a normal distribution. If I go back to 1, if I start decreasing it, then that's when it gets thinner. Okay, and I can make it really thin, or 0.5. That's the smallest I can do here. Of course, it can get smaller than that. It can't be, well, it could be 0, I suppose, in theory. Then I'd just get like a single value. In reality, we're going to get values above 0, but you can have, you could have a normal distribution with a very small standard deviation. So there we have it. These are our normal standard deviations. And if you think about it, if you look at this curve, as we change the standard deviation, it's changing the scaling factor for the area. I did ask you to have a look at that in a previous problem sheet to prove that the area was 1. And we can see we've got some transformations going on. And we've actually sort of got an fx minus transformation, and that's gonna cause a translation in the x direction. And then we're dividing x by something. That's what causes a stretch in the y direction. So linking back into earlier concepts in A-level, hopefully this is making sense, as well as understanding it from a statistical perspective. So here's a couple more. I've got 30 for both, actually. I've just realized I've not talked about this. So now we denote x. We say x follows a normal distribution. I have talked a little bit about this before, but mu is the mean, and that's one parameter. And then sigma squared is going to be the variance. And from that, we can get the standard deviation, related quantities. So that's how you define a normal distribution with its 2 parameters. And we can see from this graph, yeah, we've got the same mean in these cases, but when I get a larger variance or standard deviation, it's going to be more spread out. I've just been talking about that. Brilliant. Okay, some properties. Already talked about some of these, and actually we've proven a lot of them, but I think it's good to have it in one place. So this is a continuous random variable. It can take any value, as opposed to, say, the binomial distribution. We treat these two distributions very differently, although there are some similarities. Okay, because if you look at the binomial distribution, it's kind of going up and down. It depends obviously on your value for p, but it looks a bit like it could fit a kind of normal. But anyway, that's for another time. It's got some parameters. It's symmetrical. I've talked about this. It's bell-shaped. It's got an infinite range with asymptotes either end. Total area is 1. It's just all in one place here. And then don't forget about these facts as well. And I asked you to try and prove these in a previous problem sheet. The fact that for any normal distribution, you've got 2/3 of the values within one standard deviation of the mean, and so on. And there's some points of inflection where the gradient goes from increasing to decreasing, or decreasing to increasing. So we get a family of many different bell-shaped curves. I'm sure you can't wait to get doing some calculations with these new normal distributions. So here's an example. X follows a normal distribution with mean of 30 and variance of 4 squared. So I'm just going to write that down. Mu is equal to 30, because if you remember in your ClassWiz calculator, it's actually the standard deviation that we put in. It's written as 4 squared here, so it's a bit of a reminder, but if it's written 16, we'd have to remember to square root it. So remember to do this. And then I want you to have a go at these questions. My strong advice is to draw some sketches, because then you can get a bit of a feel for whether it's right or wrong. But see if you can do these questions here. Okay, I'm going to talk through them. So I'm going to draw my normal distribution. I've got 30. I've got a bell-shaped curve, just roughly, less than 33. So I know my answer is going to be greater than 0.5. But the rest of it, I can just get my ClassWiz out. Normal CD, lower limits, it's a less than, so it's going to be a big negative number. Upper limit, 33. This time, I need to make sure I'm not using my standard normal distribution, but this one here. So 4 and 30, and I get 0.773. Let's just do 3 sig figs. For B, similar setup, greater or equal to 24. So it's going to be to the left. I'm again going to get an answer greater than 0.5. I just think it gives a good idea of what's going on, and having a good feel for these sketches is really useful. Doesn't matter that it's greater or equal to, remember, in the normal distribution, doesn't make any difference. This time my lower limit's 24, my upper limit's just something large, 0.933. Okay, yeah, I can see that. You know, I've drawn it a bit too far to the right. Like, it should have been further this way, but like, it still gives a decent picture of what's going on. Next one. Do you know what? I'm going to actually just delete these two so you can still see the question. Okay, actually, this is in some sense easier than A and B. Because, oh wait, I'm going to go from here. So I've got 30 as my mean, and I'm going 33.5 to 38.2. It's this region, so it's going to be less than 0.5 as my answer. Okay, it's the same mean and standard deviation, 0.171. And finally, okay, haven't encountered this with a normal distribution yet. It's an OR probability. So I've got my 30, I've got 27 here, I've got 32 here. I'm interested in it being here or here. So I've got a bit to do now. It's a few approaches, and you could decide which you want to do. And you know, hopefully you've had a go at this, but you could find a probability that x is less than 27. The probability that x is greater than 32, which means you have to do 1 minus the probability that x is less than 32, and then add those together. Or we could do 1 minus the probability that x is between 27 and 32. And I think I'd argue that this is the quicker one. I think it was 32. Okay, can I store that in my memory? Yes, you can. So I'm just going to go straight for the answer. .535. And there we have it, our first set of examples using non-standard normal distributions, the same sort of calculations as for the standard ones though. Let's look at another probability question related to the normal distribution, non-standard. However, this time we're going to delve straight into modeling. So we are modeling an IQ test and it's given us the normal distribution actually. It might not always give you this, it might say it follows a normal distribution with a mean of 100 and a variance of 225 or whatever. The first step would be to write this bit down. Once you've got this, you're well on your way. Adults scoring more than 140 a class is genius. Find the probability of this happening. So I'm just going to remind myself that mu is equal to 100 and the standard deviation is actually 15. Then what I'm actually trying to find, I'm trying to find the probability that x is greater or equal to, but it doesn't actually matter for a normal distribution, so greater than 140. Once I've done that, like I've turned it into the same kind of question as previous. The lower one, 140, the upper one, just make it big. Okay, and we get a number in standard form, it's going to be 0.00383. So 3 significant figures. I might just write a few more figures down, 0.0038303. I'm going to put that in brackets just because I'm going to use that in a second. Okay, that was part A. Have a go at part B. 20 adults take the test, find a probability that 2 or more are classified as genius. Well, guess what? Guess what distribution has creeped back into this topic? This is 20 trials with a successful failure of being a genius. Probability of success 0.0038303. This is a binomial distribution. Y follows a binomial distribution. Do you know what I should say? Let's Y be the number of geniuses. I should put that in little apostrophes like they have. Then we've got 20 trials. And this is why I included a bit more, because if I want to be accurate to 3 significant figures in this question, I should really use a few more here. And then what am I doing? The probability that 2 or more are classed as genius. So it's x greater or equal to 2, and it is important I have to include 2 here. And that's going to be 1 minus the probability that x is less than or equal to 1, because this is 2, 3, 4, etc. So I do all of them, and then I need to minus the 0 and the 1 from it. So CD button, less than or equal to 1, 20 trials, 0.0038303. And then we get 0.997 as our answer. But wait, that's not the answer, is it? Because it's 1 minus that. Very easy to forget that. So store that in the memory. Okay, and I've got another really small number, 0.0000001. 0.0266. So, very small chance of that happening. Okay, hopefully you're happy with that. We're bringing back in the binomial. We're bringing modeling of the normal. We've got non-standard normal, but it's the same, it's the same stuff that you've done before. You just got to be able to recognize, actually, there's only ever going to be probably, these are the two main distributions, your normal one and your binomial one, but don't fixate on that. Focus on the parameters, what's going on, fixed number of trials. Just develop your knowledge of probability. How about this question? Actually, now we're bringing in non-standard normal distributions and we're bringing back in the inverse. That's okay. We can deal with that. Again, get a sketch down. I've got a mean of 20. I've got a bell-shaped curve. The probability that x is less than a is 0.75, so it's going to be over here somewhere. So I know my answer is going to be greater than 20. I know that I've got my inverse normal function. The area is 0.75. Oh, I rushed this, didn't I? I should write down that mu is equal to 20. It's just good practice. Sigma is equal to 3. .0. That is actually the upper quartile, if you think about it. And then B, probability that x is greater than a is 0.4, so it's going to be here. Roughly, it's again going to be greater than 20. I'm going to change this, remember, to probability that x is less than a is equal to 1 minus 0.4 and 0.6. I've turned it into the same problem as previous. Or previously, I should say. 0.6, 20.8. Okay, brilliant. Right, one more to look at. Now, I don't know whether A is to the left or right of 20, I've just realized. Can we figure this out? Yeah, I'm not sure. I'm just going to stick it. It's not actually going to matter. I'm going to stick it to the right. Okay, and then I've got this is 0.3. Okay, so there's a bit more to do this time. I've got that, therefore, that the probability that x is less than a is going to equal this red bit, but then it's also going to equal this blue bit. So it's going to be 0.3 plus the probability that x is less than 16. So I'm going to first of all have to deal with that. So lower limit's going to be large and negative. Upper limit's going to be 16. 0.09121. 0.0912. add the 0.3 to that, 0.39121. And I've again turned it into the same problem as part A. So now I can get what A is by doing the inverse normal. Let me store that in my calculator as B. Swap over to inverse normal. I wonder if I can, I've never actually tried this. Does that work? It looks like it will. And I get 19.17 or 19.2. It is actually good practice to write it to a bit more and then round it. Okay, so I was wrong. It was actually to the left of 20, but it didn't make any difference. The sketch still gave me insight into what to do. Another modeling question. This time we're given a random variable d, which follows this normal distribution. So mu is equal to 20, sigma is equal to 1.5. Given that 60% of plates are less than x, find x. So it's going to be over here somewhere. This is not perfectly to scale, I know. It's going to be here. So what am I finding? I am finding the probability that d less than x is equal to 0.6. Actually, this is just another inverse normal distribution question. .4. I think the reason I put this example in is because then it asks for the interquartile range. I just realized give a bit more space. So the interquartile range is going to be this distance here, such that I've got 0.5 of the area here. Remember, the interquartile range is the middle 50% of your data. So I've got to try and figure this out. And I know that it's symmetrical, so I'm going to have here, I'm going to have 20 plus my some value. Let's call it, what should we call it? Let's call it B. And then here, I've got 20 minus B. However, I'm overcomplicating this because if it's the middle 50%, then I can just, because I know it's symmetrical, all I need to do is this. I've got 20, and then I've got 20 plus B. And actually this area is going to be 0.25. So that's what I'm focusing on. And then if you think about it, again, even more so, this area is going to be 0.5 because it's below the median. I think there's a few ways of doing this question, but overall, I'm going to have the probability that D is less than 20 plus B is going to be 0.75. I think I could have gone there straight away, to be honest. I could have said, look, the upper quartile is going to have 0.75 below it, and I could have written this straight away. I might have even have not called this 20 plus B, I might have just given it a symbol, but I've gone with it now. It's enough though. Okay, I've got 21.011. So B is going to be 1.011. Remember, that is this length here. So finally, the interquartile range is going to be 2B and then we have it 2.02. You know what, I could have just doubled it from there. I don't know why I just did that. Okay, so slightly more awkward question. Multiple ways of doing it. You don't have to do it like I did it, but at the end of the day, that's the answer you should get.